So I was actually working in OpenStack Cloud for the first 3.5 years of my career, and then I moved to Radisys, and currently I'm working in the broadband domain. So first, I don't know like how many of you know the cloud computing related concepts and what the OpenStack Cloud and what the virtualization is. So to include everyone, I'll just start with the basic, and I hope these basics are enough to get you started. And so as and when required, you can like so. So I just this whole session of 2 hours, I want to divide it into two. So the first 1 hour 45 minutes is like I'll be presenting what the cloud and various concepts, and the later 15 minutes we can have a question and answer session. So please note down the questions whatever you have in the meantime, and we can have it in the end. Otherwise, like you can post the question by stopping me if you have like difficulty in understanding further concepts. So that's also welcome. So before jumping into the OpenStack Cloud, so I'll just want to talk about the virtualization, because the virtualization is where all the magic happens in the cloud. So here you can see, how do I minimize it? So here you can see basically 4 servers. When I say servers, these are like physical servers which will be having a disk, CPU, and RAM. So usually in our case, just to let you know what virtualization is and what are the advantages of it. So I have here 4 physical servers, and imagine like all are identical, and they have 128 GB of RAM, 64 CPUs, and 1000 GB of disk space in all the 4 servers. Now, the first one is actually working with the web server, the second one hosted app server, third one hosted mail server, and the fourth one FTP server is running on. And for the sake of simplicity to understand, so say the web server is basically consuming 20 GB of RAM, 10 CPUs, and 100 GB of disk. Same as the case with app server, mail server, and FTP server. Now, what you got is, if you take an example of web server, among 128 GB of RAM, you are basically making use of 20 GB. And though you have 64 CPUs, your application is only utilizing 10 CPUs and only 100 GB of data. So now there are two things you can observe. One thing is, among all these physical servers, you are underutilizing your resources. Second thing, you have to maintain them, and also you have to power them up. So power consumption also, usually the labs and the servers that you have, the high-end servers, they'll consume lot of power, and the maintainability of all those servers is a huge cost. So what if there is a way wherein to maximize the resource utilization, and you have all those applications that you're running in all different servers, if you can run them in just one server to the capacity of that particular server, the physical capacity of that server into just one server, and just move all the rest of the 3 servers just idle or just simply shut down. That is where the virtualization comes into picture. So in virtualization, you basically deal with the hypervisor. So the hypervisor is an application that is running on the bare metal server. So when we say bare metal server, it's a physical server that will be like having the disk space, CPU, and the RAM. And the hypervisor also manages the VMs. So VM is a virtual machines. So here you see that, where is my cursor? Yeah. So here you see this is one server, this is one physical server, this is one physical server, and this is one physical server. So you mean to say they will be running some operating system. So you're calling them some machines. So as you might have aware of this virtual machines, so the virtual hypervisor is one that actually manages all the virtual machines. So instead of like launching all of the different services into different physical hardwares, you just launch 4 virtual machines. Each of them will be having a 20 GB allocated to them, or you can give bit extra and 10 CPUs and 100 GB of the disk space. And now when you compute all those things, so you're essentially out of 128 GB, you'll be using 80 GB of the RAM and hardly 40 CPUs and 400 GB of the disk space. So in a way, you are just simply removing the unnecessary, or you're keeping away the unnecessary hardware, or you don't even have to purchase the hardware, first of all, all the three servers. And so now, by this concept, you can actually maximize your resource utilization. And it's also very easy to manage, because you just from remote location also you can just spin a VM. When I say spin a VM, you are basically launching a VM, and you can just delete it as and when you need it. And when you install an operating system in any physical server, it basically takes almost like half an hour to install all the servers. So for virtualization purpose, you will be having some different VDI images. It's not VDI, virtual disk image. It's a one extension. And then the famous one is the QCOW2. And there are different formats, the virtual machine formats, wherein you just launch the virtual machine once and you save that particular file. And next time when you launch that particular next virtual machine of that type, you just simply make a copy of that virtual machine, the VDI or QCOW2 file, and launch that. So in a way, the launching of a virtual machine time essentially it reduces to some 5 minutes, or 5 to some 6 7 minutes. It will not be even not more than 5 minutes basically. And managing of the virtual machine is also very easy, because you can just simply delete and you can spin it whenever you need it. And you don't have to go again and again to your lab to set any wiring or cabling things for your machine, the physical machine, the operating system where it is running, to manage some network related operations. Yes, Patil. Hello. Someone has raised a hand. Was that accident? Okay, okay, sure. So I hope this has cleared why what is virtualization, and what are the benefits that the virtualization actually fills the gap between the physical resources and normally what you do with the virtual hypervisor. So if you have any questions, please note down. We can have it in any discussions. So moving further, so if we go with the concept of cloud, so we'll talk about the OpenStack later. So if we take the concept of cloud, so the cloud is essentially implementing the virtualization, the disk virtualization. So whatever the virtualization you have talked here, so you will be implementing the same thing in the cloud. Now I'll just, instead of giving some textbook definition or something, I'll give a real example wherein you can understand what exactly the cloud, why you need a cloud, and what is the importance of that. So let's take an exam or election. Okay, leave the election. So everyone knows the Flipkart's what is that called? Big Billion Day. So during that time, the load on the servers will be increased heavily, and sometimes your request won't be processed. And even if the request will be processed, it will be sometimes slow, and sometimes the request will go unhandled. So now what they can do is, usually that happened the first year when they launched, but later on it did not happen that much. So what they can do is, there are two possibilities. So the Flipkart can go and buy the physical servers, and they deploy their servers, multiple servers, which can sync each other and host all the the Flipkart service on them. And once the Big Billion Day gets over, now they can just simply discard those servers, whatever they have purchased. Now, if you notice here, for a short span of like 1 week or something, the Big Billion Day lasts. They are actually investing the servers, like they usually cost lakhs and lakhs of rupees. So for a 1 week of duration, you don't have to spend the lakhs of rupees to buy the high-end servers, just to make sure that they will be unutilized after a week or something. So the other alternative is, you go to any cloud provider, be it Azure, AWS, or any other cloud computer provider, be it Google, Oracle, or anything. Buy some resources, how much ever is needed, like based on your need, and you host your services there. Once the Big Billion Day gets over, you can like lease those resources for that particular week, how many days that particular service the big billion day runs. And after your big billion day gets over, you can like come back to normal, like your normal services, and your lease gets over, and you can just pay for the lease amount of period. So here you don't have to maintain your servers, you don't have to do any of those lab settings or cabling and all those things. So basically in real world, when you go to any labs or something, these are like really very hard in managing the data center and all those things. So I hope you understood what you can do with the cloud. So there are like two types of clouds. One is private cloud and the other one is public cloud. So what we have talked about uh, just before this, the big billion day, falls into slightly in the public cloud. So when we say private cloud, you are actually hosting your own cloud service in your data center, and you manage, you maintain, and you do by all yourself. So the data center will be kept on firewall to handle any like malicious request or something, and you will be replacing as and when the servers gets outdated or something. So here, like the advantage is like since you are managing your like there are less data breach and more security because you're handling your own firewall, and that like your whole data center is sitting behind the firewall. But the other side of this private cloud is like you have to manage all things and you have to buy the hardware and every time. So yeah, that's kind of cost you have to spend. In public cloud, you basically go and go to one of the cloud providers and you tell them your requirements. You lease the services for some amount of time, and the cloud provider basically provides you all the security and everything. You don't have to maintain any of your resources. Basically, the cloud provider maintains all your resources, and your services will be running on the resources. Now the problem here is that there can be data breaches because security is not a whatever you do, there are almost like chances that the data can be breached. So it's up to one who wants to choose what, like whether they want to go for private cloud or public cloud. Then there is something called hybrid cloud, wherein it's combination of both private and public. So you can go through them as and when you get the time. So let's move back to OpenStack. OpenStack is a cloud operating system. So it was started in 2010 as a joint venture between Rackspace and NASA. Later, so many companies have joined like Google, Yahoo, and Red Hat. Red Hat, one among the largest contributors to the OpenStack. And OpenStack is entirely open source. So you can just take their code, you can tweak into them, and you can just make it the way you like to suit your needs. So when you talk about the OpenStack, okay. So when you talk about OpenStack, you basically talk about mostly dealing with the nodes. So primarily there will be three nodes: the controller node, compute node, network node. Controller node is the one that basically manages all the control related operations, and it will divert the requests that are landing onto it. So the controller node is the one where the first request lands on, and based on the request type, it will be either forwarding to one of the services that are running in the controller node, or it will be forwarding the request to the compute node or network node. So basically there can be other nodes as well. So all the OpenStack nodes, they'll be so there are like three types of networks that will be connected. Uh, the OpenStack nodes gets connected. So first one is the management network. Say you're going to launch a VM inside your OpenStack cloud. So you're basically provisioning some commands. So meaning you are managing your VM. So any search, not just managing the VM. It can be anything. You are creating a router, you're creating a switch, or you're creating a subnet, or for sort of any such sort of thing, any operation related things, whatever you do, basically they will be communicated with on a separate network, what you call it as management network. So you'll understand this when we talk about the example in the later in this session. And there is something called data network. So before jumping into the data network, the compute node and network node. So the network node basically it deals with all the network related operations, like as you see here, the DHCP, L3 agent, and some L2 agent, and other plugins will be there. And compute node is where all your virtualization happens. It's not like the network in network node the virtualization doesn't happen. In network node also virtualization happens. So it's basically a network virtualization. And so yeah, we'll come there. And in compute node, basically you see the virtualization, what we have seen earlier, the disk, storage, and RAM and CPU. So compute node is where the VM gets launched. So for the time being, say some VM has launched in the compute node, and that VM needs an IP address to be assigned. What it does is it have a series of switches internally, the soft switches. When I mean to say soft switches, they are like just like a normal switch, the what physical switch what you see outside, but they are like virtual switches in the software. So the traffic usually follows a series of soft switches, and it leaves the compute node and it reaches the network node, wherein the DHCP's application, what you call DNS mask service, and the DNS mask service, it will assign some IP address to that particular VM that got launched. So for that, such operations, or the VM, it wanted to access the data outside, meaning it wanted to access the internet from your cloud. So what happens is it first basically leaves your compute node and it follows the data network and it comes to the network node. So why it has to come to the network node? Because the L3 agent is the it is responsible for router related applications in NEUTRON or the network node. So since the router is in the network node, the data has to travel all the way from compute node to the network node, then from the external network. And this is the router that you see. This is a physical router basically of your companies or any cloud providers. From there, it will go to the internet. Now you see there is one more API network. So this API network is when your hello.
ಅದೊಂದು ಕೇಕ್ ಅಲ್ಲ.
So the API network is when like this. So the advantage of this nodes is like the nodes, each node can be sitting geographically in different locations. Say the compute node can be sitting in Bangalore, network node can be sitting in Hyderabad, and the control node can be sitting in somewhere Pune or Gurgaon. So now any user can request any operation to get or create or delete any particular resource, like say create network. So what they do is they basically issue a corresponding API. So that will be all the way going through the physical router and then to the control node via this particular network. So these are basic concepts, the different nodes in OpenStack and what they do, and different networks and their uh, how the different networks will be used. So here, like, just it's not needed basically. I just added it because the versioning of OpenStack happens like the first version is Austin and then Bexar, and then it follows like Folsom, Grizzly, Havana. Currently, it's Victoria. So all you notice is like it starts with the English alphabets A, B, C, D, something like that. The current one is the V. So that's how the versioning happens. And the example that I'm going to show here for packet tracing, packet flow will be before Havana, or you can say Grizzly, because that's easy to understand. OpenStack components. So there are like, you can refer this particular site, github.com OpenStack, to see the number of components that the OpenStack has. So it has so many components, and I have picked few of them which are very important in your service to launch a VM or to launch any service in the cloud. The first one being the Horizon. So the OpenStack supplies two user interfaces. One is the command line interface, and the other one is the graphical user interface. As command line interface is always like a bit cumbersome, or if someone novice user or some novice operator is dealing with the command line interfaces, that will be very difficult. So they provide a nice interface, graphical user interface, what you call as Horizon. So you can issue commands from the Horizon as well. And there is something called NEUTRON. So the NEUTRON is the module that implements the core networking concepts in the Openstack. We will talk them in the later sessions. Then something called NOVA. So the NOVA it manages the infra-related operations like launching a VM, allocating some resources to the VM, and deleting those VMs. Then there is something called Identity Service Keystone. So this is where all the user authentication and token validation, all those things happens. Then Heat for orchestration purpose. Orchestration, when you say you wanted to like automate some things to be happening, and you don't want to like go to the UI, create this, create that, or go to the command line, issue this command, that command after like two, like for each operation to create a network, you usually like issue one or two commands, or in like UI, you click first link, then second link, or third link, something like that. So what you can do basically, or to automate, if you're running, you're a cloud provider and you recently added some feature, so you can't just keep going and doing some manual testing, right? So you wanted to do some automation as well. Or a new customer came to you since you are a cloud provider, and he told you his requirements, and you are supposed to provide him service. So you just can't go to him and say like, okay, yeah, please wait for some half an hour or 20 minutes or some 1 2 hours. I'll just create all the resources that are required for you and something like that, right? So in that case, what you do is like you use the Heat module to automate everything. We will talk them in the bit in the later portion. So there is something called Glance, which is an image service. So in cloud, basically you launch VMs. When you launch VM, that VM can be of any type. So it all depends on the customer, right? Some customers are interested in some Linux-based VMs. Some customers are interested in some Windows-based VMs because their application run on Windows or Linux or something else, some FreeBSD or something Unix. So what we do, we have talked earlier the QCOW2 files, wherein you launch the operating system once and you save that particular file and you keep them in the Glance repository, this Glance DB. So when you are launching a VM, what you do is you go and select the appropriate VM, what you have earlier uploaded into the DB, and launch it. So basically, this is inside the OpenStack. You don't go outside and first bring that VM image file and launch it in your cloud operating system. Instead, you have a Glance application, a Glance component, wherein you first update all the component operating systems that are required, and you just launch them as and when you require. So the component communication. Now, before this, we have to talk. Since we have talked here multiple components, right? The Horizon is there. Then there is Horizon is there, Neutron, Nova, Keystone, Heat, Glance. There are some other applications like Cinder, Ceilometer, and all of the things. So there is one thing in common in everything, in all of the components. So say, for example, Neutron. Say, for example, Neutron. So can someone please turn off your microphone? So each component will be having multiple applications running in, and there is something called API server. So the Neutron has its own API server, Nova has its own API server, Keystone has its own API server, Heat has its own API server. So as Glance. So there are two types of communication that happen. One is through REST and one is through RPC. So the REST is basically to each of the API servers that are in each component. So you are from somewhere, or you are using some graphical user interface, or you're using some command line. You are requesting some resource to be created. When I say resource, it can be either like network, router, or any other VM or anything. So you basically request a command in your Horizon or through command line. So that will be like basically making a REST call to the API server of corresponding module. So when you make a request to create a network, it will be landing onto the Neutron's API server. When you request to launch a VM, the request will be landing onto the Nova's API server. So here each and when you are going to upload a operating system image, the request will be landing onto the Glance API server. So the API server will be handling the request from the southbound, you can say, or north-south traffic, you can say. We'll talk about that. From outside anywhere, you have to send any request, you will basically make use of REST server. And apart from that, each component, if the Neutron has to talk to Nova, or the Nova has to talk to Keystone, or Neutron has to talk to Keystone, so all different components, they'll be talking through REST APIs. So we'll come to the RPC, why that is there, but each component will be talking in the REST to other component, and each component will have different types of processes for different purposes, and those processes will be talking using RPC. So as all you know, the REST is basically a client server API, wherein the server basically provides operations like get, put, patch, delete, and post, and the clients will be basically consuming those operations based on their needs. So, and now come to the part of the RPC. So RPC is where like the remote procedure call. You are in process. So this is basically for inter-process communication we use here. And you are one process, and there is one more process, and you wanted to execute some procedure or a function in the other process. You basically make a request to that particular process, an RPC saying a function name. So that function name will be executed inside the other application, and it will give you the response. Whereas the response type also differs, whether it's a RPC call or RPC cast. When you say RPC call, it's like non-blocking. When you say RPC cast, it is like blocking. You are basically waiting for the response to come. So the RPC in OpenStack managed by the RabbitMQ. RabbitMQ is a messaging queue protocol, an application that works based on messaging queue protocol. So it has different types of mechanism to exchange the messages. So exchange is the word here you use to refer to different types of exchanges. So it can be a direct exchange, it can be a topic-based exchange, it can be what you call fan out exchange. So in direct exchange, it means that the producer and the consumer, it's like one-to-one communication. So there's a queue associated between a producer and a consumer, and you're just posting onto the queue, and the consumer will consume it. And in topic-based exchange, there is one producer, and there can be multiple consumers who listen on to a separate topic. Say the topic name is Nova or Neutron. So whoever the other applications or other company processes that are interested in that listening to that particular topic, they basically receive the request from that those particular queues, and there is something called fan out. So the fan out exchange is like there are a number of queues, a number of application, and a number of processes, and a number of queues. So you basically post into all of them, and everyone, like it's like flooding. Basically you are just like sending a message, and that will be reaching out to all the processes that are listening onto the queue. So this is the link wherein you can go and see some basic concepts of the RabbitMQ. So this explains quite good amount of starting steps to further debug or like to implement your own RabbitMQ related application, or your own like some IPC mechanism or something. So you can refer that site. Now let's go into different components of OpenStack. So let's start with the Keystone. So the Keystone is basically used for user authentication. So as we have discussed earlier, there is something called Horizon, which is a user interface. So it's a graphical user interface. When a graphical, so when you're supposed to enter, like when you're supposed to create or see or delete any resource, you first have to log in. Otherwise, like there will be a users gets created and you have to log in by some username and password. And once you log in using the username and password, the request will be landing onto the Keystone API server. Now the Keystone basically validates whether this particular user and its credentials are proper or not. If it is not right, then it will not let the user log in into the cloud operating system. If it is a valid user, then the horizon, the graphical uh, page will be displaying with like different icons that you will see in the next slide. And there is something called token validation. So when a user logs into the cloud operating system, he will be assigned one particular token, and the token will be having some expiry time along with the user's information, like what's the role of the user and what type of user it is and to which domain or tenant the user belongs to. So that particular token will be stored in the Keystone database, and the same token will be given to the user. Now, next time any user it want to create any resource, say a user want to create a network. Now, what happens is the first request will be landing onto the NEUTRON API server to create a network. But then the NEUTRON API server will basically make a REST call to the Keystone API, Keystone server with the token that is being supplied or the token that is given when the user actually logged in for the first time. So now the Keystone basically validates whether this particular the user's role and the user type and see whether it has a right to create or delete or do any operations on that particular resource, whatever it is requesting for. If it is, then it returns success. If it is not, then it returns false or unsuccessful. So based on that, the user will know what kind of what just happened, whether the resource will be getting created or the resource will not be getting created. And there is something called managing roles. So if you are familiar with some Linux operating system, you basically have, say, there is something called root user and there's something called normal user. So users are some different users, but they have different roles. So the root user is the one that has like ultimate power on the system, wherein it can just create any resource and it can delete any resource. It can even delete other users as well. Same is the case with here. It can have different users. It can be like a demo user or an admin user or any like different, and the roles is like whether it has a kind of permissions. So you can basically give you can define your permissions or roles and you can assign those roles to the users. And there is something called tenant. So this tenant is like kind of a project wherein each user or customer can have it, can be a tenant based on their requirements. So the next topic is horizon. If the user enters right credentials, this window gets displayed basically. And you see here the first like here in the left side project. So here is the user actually entered with the admin user, and this is the admin user and he has the admin credentials basically. And under the admin it has overview, then compute, then volume, then network and system, and in the end identity. So when you click on the compute basically, sorry, when you click on the compute, it will show you some compute related operations links wherein you can create or delete a VM or any flavor. So we will talk about the flavors and all those things in the later when the Nova is getting discussed. And a network is where when you click on the network, you will have the options to create network or manage network basically, not instead of saying create, to manage basically. It can be either creating or deleting or updating. And some security policies or routers, managing router and all those things. And the identities where we have just talked now, wherein you can create the users and roles and tenants and all those things. So this is how the horizon window looks like, or the page looks like. Next, come to the Nova. So there are two key components in OpenStack, Nova and Neutron. Nova basically manages the infrastructure, and Neutron handles all the network related operations. So apart from these two, there are other operations like they are like, it's not like they are not so important, but their task is like very minimal. Like the glance, what you have seen earlier or what we have discussed. Its job is to like maintain the images or the operating system images and provide the image as and when the request lands onto it. And otherwise, like it will be just staying there. And there is something called celometer. It's for monitoring purposes. So if I'm taking a service from the cloud provider, he can give me like he can have the celometer which can monitor like the kind of requests that are landing on, like how they monitor it, like how they make the money based on number of requests or how again, so they configure that. There are different components, but yeah, the Nova and Neutron are the two key components. And when you see the Nova, this is what the Nova's architecture looks like. So there are different components you see. The API server is the first one, and there is something called conductor, then scheduler, then the compute. So also the keystone is there. Network is, when you say network here, it's actually a network node basically. And there is something called hypervisor, glance, and sender. So we'll talk about one of all of this like one by one. So each time a request comes to manage a particular VM, the request first will be landing onto the API server. And as we have discussed earlier, when the user logs in, he will be assigned a token to him. And so any request landing onto any OpenStack module, it will be first, the first request from the its API server will be going to the Keystone service. This is to authenticate whether the user's token is like whether the user's request is valid or not. And then what the API server does is, so there is something called here RabbitMQ queue, which is not shown here in the picture, but all you can see is here the this kind of what do you call it? Dark arrow, that's Oslo messaging. So the RabbitMQ basically uses the Oslo messaging to exchange the request RPCs basically. So as in when the API comes to the when the request comes onto the API server, it basically validates that, and then it puts the request into the RabbitMQ's queue. Now once the request get once the request updated gets updated into the queue, the scheduler is the one. So when the request comes, the API basically adds an entry related to that particular request, and it puts the request into the queue. Now the scheduler picks up the request from the queue, and it will fetch the corresponding information from the DB what the API actually wrote earlier. And it also gathers other information about like on what compute nodes how many resources are available, like the number of CPUs and the RAM and the disk space. And it does the scheduler does basically some kind of filtering and weighing as to decide basically load. This is kind of load balancing. So it basically decides on which compute host this particular VM has to be launched, and it updates the corresponding information back to the database, and it puts the queue request into the queue. Now the Nova compute, it actually picks up the queue. It actually picks the request from the queue and requests the conductor saying, fetch me this particular VM's details. So it will go and fetch all the information that were updated by the scheduler and give it back to the compute host. Now the compute actually decides. Now the compute knows like how much RAM or CPU or disk has to be given to this particular VM that is going to be launched. And here one thing to be noted, the compute is like hypervisor agnostic. When we say hypervisor agnostic, there are different types of hypervisors. So the most of the Linux machines comes with the KVM hypervisor, and there is something called Zen VMware's hypervisor, and then like Hyper-V from Microsoft, I believe. Yeah. So there are different types of hypervisor. So this compute node is like agnostic to the hypervisor, so it can work on any compute host, a hypervisor basically. So in the process of that, when the VM gets created, it requires that particular VM to be having an IP address assigned. So it will talk to the network node, and before launching the VM, it needs that VM's image type to launch the operating system. So it basically contacts the glance to give it a that particular image. So it will like bring in the image, it talks to the hypervisor. Let's say in case of KVM, it will be talking to some KVM library in the kernel, and the KVM library is the one that actually launches the VM. So this is how the Nova's communication happens, and the Nova's different components and their operations, what they do. Now coming back to Neutron. Just 1 second. Excuse me. So when you say normal network in the real world, usually just imagine the college lab or college lab. So when we say network, so basically the network starts with your machine or your desktop in the lab that will be connected to one of the switch, wherein some network will be configured, and this switch will be having connected to all other different machines or desktops in the same lab or different lab, and also the switch will be connected to the router, wherein the router can be connected to some other routers. So that is how the whole network gets formed. So for that, here if we notice clearly, so we require a network, and we also require subnet to be configured. Then we require a router, we require a VM, and there is something called a port that will be connected to the switch and the computer. And if you need, your router can also support firewall service. So basically the routers are the one that actually host the firewall services, and usually and VPN services as well. So it's not like the switch can't do the firewall service, but yeah, usually the router, because router is the CPE, basically customer premise device. And there is something called a floating IP and fixed IP. So they came into the picture when the network gets virtualized, the entire networking concept virtualized in the OpenStack. So as you know, the network is a entity. It's not a physical entity basically. It's just an entity which can hold a number of subnets. That you can create in the Neutron. And there is something subnet wherein you can assign a particular subnet, or you can give a pool of IPs that can be utilized from the particular subnet. And you can also create a soft router wherein the subnet actually gets hooked into the router, and the other side of the subnet will be hooked in your VM. And there is something called a port. So this port we actually come to later slides. It actually has so much something it has to do with, like it has involved in more operations. And there is so also the Neutron supports like the firewall as service, VPN as service, load balancer as services. So they will be implemented inside the router, usually in outside world. But when it comes to the OpenStack, for a router, you launch an operating system. There is something called VYOS or Viata VIOS. So this is a router operating system wherein you configure your router related instances in that, and you also configure the firewall related rules in that, and you can also configure the VPN related configurations. So the Neutron also supports them. And there is something called floating IP. So floating IP is like a public IP address that can be reached from anywhere to anywhere in the world. Fixed IP is like a local network's IP address that will be reached within the LAN and not outside of that. If it has to, then there will be some other floating IP that will be like NATed to that fixed IP to access any other information or outside world. So these are different components in Neutron. So basically there is some Neutron server, then Neutron DB. Remember, when we say database, each component will be having its own database. So the Nova we have talked earlier, the Nova will be having its own DB, and Neutron will have its own DB. Glance will have its own DB. Keystone will have its own DB. So different components will have its own DB. And there is something called messaging queue, what we have missed in the earlier Nova's thing. And there is something called L2 agent, L3 agent, DHCP agents, and advanced services. This advanced services is what we have discussed, like firewall, VPN, and load balancers. Now, any requests? So the job of this L2 agents is to deal with the layer 2 functionalities. Hello. So L2's job is to deal with the layer 2 functionalities like switching related operations. And L3's job is to deal with the routing related components. So when any user creates a router or soft router, it basically the request will be landing onto the Neutron server. And from there, the Neutron server actually puts that particular request into the message queue. So remember, every request that is coming in to create any resource, either it is network, subnet, or port, or the router, the first there will be an entry that will be added into the Neutron DB. Then it will be posted into the queue. And since these agents are subscribed to the queue, they'll be receiving those corresponding requests. So when the L3 agent receives the request of creating a router, the L3 agent go and create a namespace for the router. And that namespace for the router will be acting as a router for the network that will be hooked in. Same is the case with the L2 agent. When the request comes to create some network or subnet or to port creation, they will be first added into the Neutron DB. And then the same message will be posted into the RabbitMQ, the message bus, queue bus. And then since the L2 agent has subscribed to such a topic or what you call exchange, it will be landing over here. So yeah, we'll go. So these are the components. Like this is not like it will be like understood very easily. So the networking in the OpenStack or the Neutron is done like a really different way. So it involves in multiple different advanced concepts. So I'll try to explain it as much simple as possible. It's okay if you don't understand. You just go and read about them. So usually any networking services, what you see in the real world, or you take a switch. So the switch basically has two types of components. One is the control plane and the other one is the data plane. So when any request is made to the switch, wherein different computers are connected in the network, and one computer is accessing for some particular who pinging or some access, wanted to talk to some other computer in the switch that are in existing in that network. So first it will send an ARP request, then the switch will flood that particular ARP request who has this particular thing. And once the guy who has that particular MAC address will reply with that, hey, I'm here and this is my MAC address. So what the switch does is now its control plane basically observing all those things, and it puts those rules saying that this particular MAC address is onto this port and this MAC address is onto this port. And next time if they wanted to talk, now this time they don't send any ARP request. As in when the request comes to the switch, it knows that okay, this is a so the switch actually sniffs the source and destination MAC addresses, and checks the MAC table. If it finds the corresponding port that already getting updated, so it will directly forward it to that port. So this is like the control plane is the one that actually learns these flows and the request, and like later on it will not like basically here the control plane is for the learning and the data plane is for like once the control plane learns and pushes the flow, the data plane is like follow the flow and talk to the other guy or other computer in the network or different network or whatever it is. So this is how it usually happens, or in traditional networking this is what happens. But now since this is not so viable, like if you have thousands of switches, imagine, and they are into different locations, going and configuring each of those switches is really a big task. What if there is a way you will be sitting in some central location and you can just manage all those thousands switches? It's not just with switches, but you can also configure some routers as well, some basically a networking component. So this is where the software defining networking comes into picture. What you call is SDN. So wherein there will be one control plane, and there will be like a bunch of data switches or some like hardware computer devices will be there. So you basically don't involve the control plane or the brain of the switch into the switch, but basically you take it out and you keep it somewhere that is available or visible to all other switches and any request that is coming onto the switch, the first packet will be forwarded to the controller node. Now the controller node has the topology of the whole network, so it knows where the packet has to go, and it basically pushes the flow back into the switch. And next time similar packet request comes, it will not be going back to the controller node. It will be like simply forwarded to the next machine whom it wanted to talk to. So in this way, you are basically reducing the operational cost and yeah. So you don't have to go and configure everywhere. You just take that out, and now the control plane, that is like instead of like having so many control planes and configuring so many rules in those control planes, you just simply configure in one control plane, and this control plane can manage all of those things. So this is where the SDN, like essentially what SDN does in an overview. If you need some detailed answer about that, you can actually go and Google it. So basically, the OpenStack Neutron, it heavily relies on the SDN concept, and the backbone of the OpenStack Neutron networking is the Open vSwitch. So let's keep this ML2 plugin, overlay networks, and all other topics, and first jump back to the Open vSwitch. So Open vSwitch is an application that runs as a kernel module, and it implements the OpenFlow protocol. So the OpenFlow protocol is the one that actually deals with the SDN concept. So based on the requirements, the Open vSwitch actually creates instances. When we say instance, it is basically creating soft switches where the the VM that gets launched, its IP or port will be hooked into those soft switches. And these switches will be configured with the open flow rules. So usually those rules will be like, if any request coming from this particular port, you forward it to this port. It's like, I'm just telling you simple, but there will be like bunch of tables wherein if request is landing onto this, and if the packet is of type R, then it has to go to some table 21, and if the packet is on the table 21, it can be going to some other table. So like there, like, based on the packet type also, there will be a number of tables wherein the Open vSwitch manages. And essentially we have in OpenStack 3 types of switches that will be created by the Open vSwitch and managed by Open vSwitch. Hey, just 1 minute. Hello. Hey, good morning, Hari. Uh, yeah, I can talk to you, but can I call you after 12 o'clock? I'm in the middle of something. Okay, sure. Huh. Hmm. Yeah, I guess whatever I have done, we have checked it, and Chandra actually pulled out from that, right? Yeah, yeah. Which when you say Chandra, you're talking to this MP Chandra or Ramayanam? Okay. Yeah, you can talk to Ramayanam. He's the one who actually put the ERPs. Sorry for the disturbance. So, so in OpenStack, you basically the Open vSwitch creates 3 instances and manages those instances, adds, deletes the flows based on the number of networks gets created, and attaches the VLANs, VXLAN IDs, and all those things. So here, those 3 instances, what you call is BR int. It's an integration bridge. Yeah, we will talk about it more later, or if not, the time permits, you can go and read it. Then there is something called BRTON, the tunneling bridge. And there is something called BREXT, that's an external bridge. And apart from that, there is also something called Linux bridge. So this Linux bridge is also a switch, and this is a Linux kernel's utility. So it's not part of the OpenV switch. We needed this Linux bridge because we wanted to apply some firewall rules of the traffic that is going out of the VM and coming to the VM. So unfortunately, on OpenV switch instances, you won't be able to apply any firewall rules. So they added one more Linux bridge between the VM and the integration bridge. And then, yeah, there is something called a network namespace. So a network namespace is kind of host. When you say host, it's kind of computer. So it just like it will share your computes resources, but it's like isolation, like what the Docker or those concepts have, right? So it runs in your computer. It utilizes all your kernel's capabilities, but it will be running as an independent process. So there can be a number of network namespaces that you can create. And for better understanding, you can refer to Google basically, or we will talk in the end if there is a time. So there is something called ML2 plugin. So this is module layer 2 plugin. So earlier there were different plugins basically. So to handle, so we have like the core operating system of the OpenStack, the core networking concept of the OpenStack are realized by the OpenV switch, but there can be Open Daylight as well. The Open Daylight is from the Cisco. So like that, there can be different those networking components in the Neutron, and for each of them, earlier they used to have different plugins. And at one after like Mitaka or something, they have actually changed that. Like they created a generic plugin wherein that can handle they can create any number of they can create any number of it can accommodate any number of this type drivers basically, like OpenV switch or Open Daylight, but only one plugin will be there. And there is something called overlay networks. So to understand this, you just imagine the lab network concept what we have talked about. Now in the lab, there were like three machines, and one of them is a cloud controller, and one is a compute node, and the other one is a network node. Now, so here you are seeing two networks. One is the physical network, and the other network is like different networks that are getting created in the cloud. So when you say in the cloud, so you are basically creating some soft switches, soft routers, and soft networks and soft subnets. So this is like already there is an existing physical network, and you are creating one more networking on top of the existing physical networks. So the networking that happens inside the cloud is called overlay networks, and the physical networking what you generally see is called an underlay network. So when the packet in the eventually that has to go by underlay network, so there is something called tunneling, wherein the VXLAN comes into picture. So what VXLAN does is it assigns some tag. So there is something called VXLAN tags or VXLAN IDs. So each network will be assigned some VXLAN IDs. So if any packet that's going from the OpenStack overlay networks to the underlay network to talk to something else outside the cloud operating system, or it want to access some resource which is out of the cloud, or it just want to Google. So such request, what happens is that particular packet will be completely wrapped into the underlay networks, use source and destination MAC addresses and all those things along with the VXLAN ID. So that is where so it's not just a VXLAN. There is something called GRE as well, but most of the time the VXLAN gets used. And there is something called VETH pair. So usually, if you have to talk to from so there, VETH pair is like a pipe, wherein if you pour water from the one end of the pipe, that will be like coming out of the other end. So the same way, in a VETH pair, if you send the data from one side, it will be basically coming out of the other side. There is no routing or any networking constructs required between. So this basically comes into picture between the Linux bridge and the Open vSwitch instances like the brint and all the other things. Between brint and brturn, you will have them. Between brturn and brext, you will have them. Not basically brturn and brext, brint and brext. And yeah, so I guess we can move further. For detailed understanding, I guess you can go through the OpenStacks. The OpenStack is like having so many full detailed documents regarding different APIs, different concepts, and different components architecture. I guess you can refer, and there is other blogs as well, wherein you can understand these concepts very well. Now comes to the heat. So earlier we have discussed something called automation. So we'll talk about the same example what we talked earlier, like you got a request and you have to create like a launch some 15 12 VMs, and then there are like a bunch of 15 12 network and routers and all those things, and you going them and creating manually from the horizon or the command line. It's like a big pain, and it will take a lot of time. Like it's basically a time constraint. So what you basically do is you write some template. The template is like a format, that is YAML file. So you give the number of instances or the number of instances of that type to be created in the file, and you supply that file the heat engine. Now this heat engine talks to the various components in the OpenStack, and it will realize those resources in like less than like what you do usually. It will be very basically pretty fast than what you do. Like when you do manually all those things, it will take almost like a 2 hours or something for those many resources what we have talked earlier. But through heat orchestration, it will be like pretty fast. In some 10-15 minutes, you will be able to almost create everything. So here is the command. So what you do is like heat stack create. You supply the file, and you can give the network ID or any parameter that you want to override, like to be overwritten from the heat template. So the YAML file is what you call a template, and otherwise, like you can simply ignore this particular parameter and just simply supply the file, and it will create all the default names you supply in the template. It will take that name and create the resource with that name. So let's take an example in this template. So here you have parameters, and one of the parameter name is image name. So its type is string, and its value is like zeros. So this zeros is a QCOW2 file or a operating system file. So that comes by default with OpenStack to test anything that is working properly or not. So like it's like it will be like around 15-12 MB. And then there is something called network ID, and you are giving the default network ID name is demo name network one. So imagine that before that these things have happened already. Otherwise, like you have to write to create this network name as a demo network and upload this particular image or something, zeros or something. And now coming to the resource. So you are creating instance name. When we say here instance, we are calling it as the name of the resource of type Nova. What is that server type? So the Nova's resource, the server when you are going to launch. So its name will be like my underscore instance one. And what and all it requires an image, because the operating system from where the image has to be loaded. And there is something called flavor. So here it's like m dot tiny. So there are like m dot medium, m dot normal, and m dot large and extra large will be there. So when you say m dot tiny, it is like one CPU, 1 GB RAM, and some 5 GB of hard disk is there. So for like as in when the this parameter like the tiny, medium, large, extra large, it varies. For extra large, say it can be like 20 CPUs, 20 GB RAM, and some 500 GB of hard disk, something like that. So you have to mention the flavor based on the your computing power, like kind of service that you are going to launch. And every VM or the physical network, you always imagine the physical thing. When you launch a VM, you basically connect to some network, right? So for that, you also have to supply some network. So what is that network? It's telling go and get the parameter of network ID. So here the network ID is like demo network. When you supply this particular template to the heat engine, it will basically launch you a VM with the name my instance one, and the VM is of type tiny, so it will be having only one CPU, 1 GB RAM, and I guess 5 GB of storage. And it is expecting that, where is that? This get parameter, image name, and network ID, they should be present before. Like already it should be created before that. So here is a VM launch, and it has bunch of documents, so I did not basically add them all those screenshots over here. Uh, I just share one more document. Yeah. So basically, you log into the Openstack UI dashboard and you supply the username and the password. And like here are the steps to create the network and subnet. So you can just Google around. You'll also get them. But this was actually captured by my friend in the lab. So this, remember the earlier Horizon page when we loaded, we have seen there is something called network, compute, and all those things. So when you click on the network option, you will be having the bunch of options to manage the resources of type network, resource, routers, security gateways, floating IPs, and trunks. So when you click on the networks, here you have create network. So when you click on that, you can just give a network name and enable admin state. So this is important because if you don't enable, then the L2 related functionalities will not be working for this particular network. Basically, switching thing and DHCP and all. Then basically each network will should have a create subnet. So you enable the create subnet and then click on the subnet. Here, give some name to your subnet and give a subnet pool. So basically, you are giving 3200/24, wherein some 254 machines or VMs can be launched in this particular thing. So this IP is of type IPv4 and the gateway IP. So leave this blank so that when you attach this particular subnet to a router, it will be taking the first available IP address, say 320001. So it's always better you leave this blank so it will choose what IP it is available that time, and it can take from there. Then just click on subnet details. Just click on enable DHCP because any VM that is launched in this particular subnet that has to have an IP address, and then click on create. So here it says that the create demo network has been the demo underscore network one has been created. So in the same way, you can actually create a demo network two. So when you create the demo network two, the earlier one what we have created, it is showing that the network is already present with this particular IP address. And remember, so okay, I forgot to tell you. So we are launching VM. So we stopped it here where the VM launch is there, right? So when you launch a VM, imagine this is a computer in your lab again. So your lab, when you create your computer in your, when you have a desktop in your lab, basically you have switch, you have router, and the switch is actually connected with the router, and also the switch will be connected to different machines, right? So now just take this similar concept and apply that into the cloud. So first you require a network there. So you create a network, and you require a subnet, and the subnet need to be configured with some subnet IP pool, and you give that as well. The subnet should be, there should be some DHCP server running for that, so that it can assign a IP address to your VM. So you enable the DHCP as well. Now you require a router. So in the same networks, this drop down menu, click on the router option. Here you get a create router option. Just click on that, give some name, enable admin state, otherwise the L3 functionality will not be working. And you can select here external network. So when we say external network, it's like your computer's the outside gateway, wherein if you enable, you supply, if you take this, give this network, it means that your VM that will be launched in behind this particular router will be having an internet connection basically. And click on create router. And once a router gets created, the admin state should be up, and you have to add interfaces to the router. So what you do is you click on the router here on this demo router name. So it will open this prompt, and here you click on the interfaces. Now click on add interface. So when you click on add interface, it will tell you to select the subnet. Here the subnet what we have created earlier, the demo subnet one, you can select them. So here it is showing this demo network one and the IP address what we have, the MAC we have given. So so this subnet is under this particular network, and this is the IP pool that we have given. And click on submit. So here you see that it's active, that interface, and the admin state is off for that. Now that you have the router, subnet, and network got created, and the subnet is actually hooked into the router. So you have to launch a VM. So earlier you were here in the network options. Now go on to the compute and click on this compute drop-down option. It will open overview, instance, images, and key pairs. So here, when you click on the images, it will show you the number of images that you have in your machine, like those what we have talked about, the QCOW2 images. And click on the instances, click on launch. Now give some name to your VM. Here the count is like, if you have to create a VM of such type in like number of like VMs, like say 10 VMs or 20 VMs, then you increase this count to 10 or 20. So when you launch the VM, at a time it will be creating 10 VMs or 20 VMs of such type. Then you select the source of the image here. So currently this OpenStack deployment has only one VM, 0s, the QCOW2. So click on the arrow button so that it will be selected. Now select the flavor, like how many, this flavor is where you are going to allocate the number of resources to the VM that is going to get launched. And when you select the flavors, you see here M1 tiny, small, medium, large, extra large, and with Thunder Max. So this is like it's a custom image that was this is a custom flavor that was added basically for the company requirements. And you see the tiny, it has one CPU. Sorry, I imagine it is 1 GB, but so 512 MB of RAM and 1 GB of disk. And then small is having one CPU, 2 GB of RAM, 2 GB of disk. So different, like based on your requirements, you can choose one of the flavors. Just click on the up arrow mark. It will select that. Now click on the network. In which network it has to be launched. So you have bunch of the networks. So earlier we have created demo network one, and then this demo network was not shown, but yeah, it was written there that the demo network was created actually. Click on one of the networks, the up arrow key, and that network will be selected for you. So you see, as in the earlier slide, it was clicked here on the demo network 1, and the demo network 1 was selected for you here. Now click on the launch instance. Once that comes, you will see like demo VM1 image type 0s, and the IP address that it got assigned is 34.1.0.20. So earlier when we were mentioning the subnet there, it was 32.0.0.0/24, but this guy, it seems like he has like, after that he created one more network of the same name and changed the subnet type. And the flavor that you are given here, the status is currently active, availability zone is NOVA, and the power state of the VM is currently running. So to go into the VM, you just simply click on the demo VM1, and so this guy we have here, he launched two VMs. So one is this demo VM2 and demo VM1 in two different networks basically. And once you click on one of these VMs here on the demo VM2 or demo VM1, so it will open this particular prompt, like it will open a console for you. You just log in. The default names will be username is 0s and the other password is cupspin, some smiley. So you log in both of the VMs, and you see here that both of these VMs have already assigned some IP address, and we have also created a router basically, and these two subnets are assigned to the router. So when you ping from one router here, you are able to ping to the other guy. So you see the ICP traffic is actually working. So this is how the VM actually, like you launch a VM and what are all the things that go in between to launch a VM. So I'll come back to the slide basically. Yeah. So here you see the VM launch option, which we have just now seen. So now comes to the part where like you wanted to know. So why I'm focusing more on this Neutron related stuff, because it's very really hard to debug unless you know the flow and what all the instances that involve inside, and how the packet flow happens. So relatively compared to other aspects, the network related cooperations here, debugging, it's like very important. And then there is something called NOVA, what we have discussed. So like you will see some problems, but yeah, comparatively, the more focused is the packet flow here. Because once the packet is not reaching from one VM to the other VM, you have to go inside the virtual switches created by the Linux bridge or by the Open vSwitch, and you have to see in each of the interfaces where the packet is reaching and where it is not reaching and all those options. So there is something called east-west traffic here. You see where my cursor is moving in, and there is something called north-south traffic. So when you say east-west traffic, it means that a request from one VM in the OpenStack is actually going to the another VM in the OpenStack or inside your cloud. And when you say north-south traffic, request from the VM in your OpenStack is actually going out to the internet. So that's what you call is north-south. So even in the east-west, there are two scenarios. One is when two networks, two VMs are in the same network, and two VMs are in different network. So there can be possibility that there are two VMs, say, and you have two networks. So one a VM that got launched in network type 1 will be launched in one compute node, and network of type 2 will be launched in compute node 2. So it will not be like that. So the scheduler basically decides where the more resources are available and it launches on there. So how internally the packet flow or packet forwarding happens is what we are going to see. So here, basically there are like two instances in the same network, but they two instances got launched in two different compute nodes. So the first one is here is the compute node 1 and here is the compute node 2. And remember earlier we were discussing about the tunneling bridges, integration bridges, and all those things. So they come into picture here. The tunneling is basically a tunnel. When you say tunnel, it's like you are encapsulating something. So the VX LAN, what we have discussed earlier, or the GRE is also for encapsulating. So the encapsulation and encryption both are something different. In encapsulation, you basically treat the entire packet of the overlay network as a payload to the new packet. In case of encryption, you encrypt the entire packet of overlay network and put it in a different packet. So the entire packet becomes your payload, but that is an encrypted one. In case of the encapsulation, you can see the inside packets IP address as well when you TCP dump or you use some Wireshark or some other tool to capture the packet. So first one is the instance one that is launched in compute node one. So these images, the next subsequent images, you can find it in the open source, the OpenStack's website. I just picked up, took the screenshots from there. So the instance one is launched in the compute node one, and the instance two has launched from the compute node two. Now, if instance one wants to ping instance two, what happens is there is something called tap port. So what we were discussing earlier, when the request comes to the Nova, the Nova creates something called tap port, the libvirt library in case of KVM hypervisor. So this tap port basically gets wired using the Neutron's L2 wire, L2 agent to the instance one. So any traffic that is going out of instance one, it will be coming onto the tap port. And here we see that there is something called Linux bridge. And we have seen, we have told earlier that on Linux bridge, the Linux bridge came into picture because we wanted to filter out the traffic that is going out of the VM or coming to the VM. So inside the Linux bridge, some firewall rules will be applied. So say if the traffic is obeying the firewall rules, then it will be coming out of the QVB port. So this is like VF pair, what we have talked earlier, wherein like it's just a pipe, whatever you put in here, it will be coming over here. So this is like, that is coming into the integration bridge. Now imagine this particular VM on a compute node has two more VMs. So that will be like here instance 2, Linux bridge 2, and that Linux bridge 2 will be connected to the integration bridge. Instance 3, Linux bridge 3, that will be connected back to integration bridge. So the integration bridge name is like, it will integrate all of those traffic that is coming from different VMs into the same integration bridge. So in the integration bridge, the OpenFlow will apply some, the OVS will apply some OpenFlow rules. And based on that, it will decide where the packet has to go. Say, since our requirement that we are talking about, it has to go in the compute node 2, it will take the patch turn. So this is also with pair, as far as I remember. And then it will go into the tunneling bridge. And this tunneling, wherein the some encapsulation happens here, and it lands onto the compute nodes interface, the physical interface here it is. And from there, the tunnel VXLAN or GRE tunnels happens. And here again, it reaches whatever the encapsulation happened here on this tunneling bridge. The decapsulation happens over here on the tunneling bridge. And from patch into to patch 10, it will be going in the integration bridge. Now from integration bridge to Linux bridge, here some firewall related rules will be applied. And if it is obeying the firewall rules, the packet will be reached to the instance 2. Please let me know if this is like going overhead, because all these concepts are like telling in one day, like I don't know whether it will be really understandable or something. And there is something like east-west traffic, wherein instances of different networks. So earlier, this instance and this instance are in the same network, and this instance, is there any cursor? Yeah, instance 1 and instance 2 are in different networks, and they are in different nodes as well. So when two VMs or two machines in the physical network, if they are in two different networks, so basically they will be going their respective switches, and from there they'll be going to the router. The router decides where the packet has to be forwarded, and from there, like it will be going to the switch of the other guy to the from switch to the VM. So this is the same thing happens over here as well. So the instance one, the packet comes, the Linux bridge where the firewall rules and the integration bridge, some flow, open flow flows will be applied. And from tunneling bridge, where is this? Yeah, from tunneling bridge, some VXLAN, some tunneling happens. And now instead of going to the VM2, this time it goes to the network node, because network node is the one that is actually handling the router. So from its tunneling bridge, it comes to the network node's tunneling bridge, then to network node's integration bridge. Now it comes to the router namespace, basically. From router namespace, again, the router actually forwards the packet. So again, it will go back to the integration bridge, applies a rule, and sends it to the tunneling bridge. From tunneling bridge, it will come back to the tunneling bridge of the compute node 2. From there to the integration bridge, the next bridge, and instance 2. So the routing happens basically in network node. So this is before Havana, the version. So the drawback of this thing is, say the compute node 1 is sitting in Hyderabad in lab location, and compute node 2 is also sitting in Hyderabad as well. Now imagine the network node is sitting in the Bangalore. So since these two compute nodes are just sitting side by side, still the packet has to go from Hyderabad to the Bangalore, and they route it again and come back to Hyderabad and launch it to this VM. So like here, the packet traversal is taking too much time. So what they have come after this version of the OpenStack is, they came up with DVR, distributed virtual routing. You can go through basically. So the DVR, what it does is, like, instead of like routing, running this router namespace in compute network node, just replicate the same router namespace in compute node and compute node 2 as well, so that the packet don't has to go in the network node. Instead it will be like routed here in the compute node, and it will be directly forwarded to the compute node 2. And when the packet is coming out of the compute node 2, it will be routed here in the compute node 2 first, and then the packet will be directly going to the compute node 1. So in the image you see like different lines, but they will be connected to different Ethernet networks, basically the physical network. So each VM will be having, each host will be having two networks. For one is for management, and other one is for data network. And this is like a north-south flow, wherein the IP is having fixed IP. So here is an instance, it's having some fixed IP, say some 10.10.0.0.5, and it has to go out. So what it does is, like, it will come all the way from tunneling bridge, and it will go to the network node. From network node, it will go to the integration bridge and the router's namespace. So in router's namespace, so there is something called floating IP. So the floating IP is the one that actually is a public IP that will be reachable from anywhere. So here, what the router namespace does is, it will encapsulate the packet. I mean, not encapsulation, basically natting the packet with the fixed IP to the floating IP. The source NAT happens, and there it goes to the integration bridge. From integration bridge, it goes to the external bridge. So the purpose of external bridge is to have external access, meaning the outside internet. So from external bridge, it will be going out to the outside. So if it is like a floating IP, the situation will be different. So instead, the router namespace will, like, it will be having in your, like, this is image is not the updated one, but it will be having in your namespace only, your network node, compute node only, and this router namespace will be existing in your compute node itself. So here it will have the source NAT happens, and it will go from the compute node instead of going it to the network node. So the one last thing, this packet flow of DHCP, what we have launched earlier, right? So we just talked about the flow, but we did not talk anywhere regarding the DHCP. So in the DHCP, when the VM actually requests for an IP address, say the VM is this one, and so first from the VM, it will be going to the Linux bridge to the BRINT, then to BRTON hypervisor. So this is a tunneling, some GRE tunneling they are using, and then Ethernet too. So this is the physical, as we have what we have talked, like data network has this. Data network is a physical interface. From there, it's moving out of this compute node, and it's going to the network node and entering the network node. Network nodes BRTON, network nodes BRINT integer, and then integration bits, then to the DHCP namespace. So the namespace will be running a DNS mask service. This is an application which will give you an IP address. In the it will follow the reverse path after fetching the IP address. So now we have talked like the OpenStack is a multi-node. There will be a controller node, and there can be like not just one. There can be multiple controller nodes. There can be multiple, so many compute nodes, and there can be so many new, new network nodes as well, because they want to support the high availability and all those reasons. So isn't it not possible to do all of those things in same node? Yes, you can do actually if you have good amount of resources. So you can have all the network node related capabilities, compute node capabilities, and controller node capabilities. All of those things you'll be having in same node. But then like this OpenStack actual deployment, it's like kind of cumbersome to launch each time. Like it will take some time. So isn't there any other way to test if you have any application and you just want to test it actually? So there is a way is what DevStack. So this is also from OpenStack. This is to test your application first in your local machine. So this is like very minimalistic version of the OpenStack. Like it's when we say minimalistic, it is not like in terms of features, but like it will consume very less resources. So you can test over here. You have the document over here that you can click on, and that will go to the DevStack. You can install it in your machine. I guess it will be requiring very less resources, and you can actually play around what we have discussed. So yeah, you can ask the questions. Uh,
Hello. Oh,
yes.
thank you for introducing us with virtualization and nodes of OpenStack and sharing the steps how real-time launching will happen with VMware. Thank you, sir. If you have any questions, participants, please ask, or you can put a question on the chat box also. Hello, sir. From my
Yes.
side, one question is there, sir. So, in a communication, we'll use REST and SOAP. So, which one will
Right.
be the best? REST will be the best, or SOAP will be the best, and why, sir?
In OpenStack, you're asking, or you're asking generally?
Yes, sir. OpenStack also, sir.
In OpenStack, I don't think we use SOAP or something. First of all, I'm not so
Okay.
familiar with the SOAP basically, but as I've mentioned earlier, the REST calls, right? They'll be used for different purposes. So you have two types of communication interfaces, like the command line interface and the OpenStack in Horizon interface. So those requests will be basically transformed to REST calls, and they'll be landing on the controller node. That is one thing. And then the intermodules, the communication between different components of OpenStack. So if a neutron wants to talk, say when the VM getting launched, the VM, so this we did not discuss, but yeah, so you cannot discuss everything in this session, in this time frame. So when the VM gets launched in the OpenStack, the basically Nova Compute actually request to the Neutron server to allocate an IP address to this particular VM. So how that happens is the Nova Compute basically sends a REST call to Nova Neutron server. So it basically lands onto the Neutron's API server, and the API server internally makes an RPC to its different components, and the DNS mask service that will be picked up from picks that request, and it will like give the response. So internally between the processes of an OpenStack component, it will be an RPC that will be like realized by RabbitMQ. But between the components, between different components, say it Neutron or Nova, Keystone, Glance, Cinder, Heat, or anything. So that's like REST call. The like the purpose of this is because the OpenStack is modular Reason being that you can launch, say, Nova in one particular computer or one machine, and you can launch Neutron in different machine, and they can be geographically in different locations. So making an RPC call that long is, I guess, that is not a so feasible solution. So they have come up with this REST calls. And coming back to your question of the SOS, what is that? SOC, SOP. That actually I'm not so aware of that. Like basically, I never seen any such SOAP request anything inside the OpenStack.
Okay, sir. Thank you, sir. Any questions from participant side? Okay. Thank you for all. I hope all participants received good amount of knowledge from you, sir. Once again, I thank you for giving your valuable time. Thank you, sir. Uh, uh, Already
No problem.
in chat box, we shared the link for attendance. Kindly give your attendance, all participants, and I request all to leave the session. Thank you, sir.
Thank you so much. Thank you all. Thank you so much. Bye.